So welcome to yet another session. In the last session we started with phase plane analysis, and we defined that phase plane is basically a portrait between uh, the two states of a system x1 and x2. Why 2? Because we restrict our phase plane analysis to second order dynamic systems. We can extend the phase plane analysis to third order, fourth order systems, higher order systems as well, but it becomes complex. So mainly the phase plane analysis has been restricted to second order systems for analysis for purpose of defining stability, for finding out the type of response of a system, and so on. So we took examples of linear systems. Now continuing with actually the behavior of linear systems, we'll try to see the stability of a linear system and how it is related to that of a phase plane, how we can actually plot, how we can actually understand from the roots of a system what type of portrait we'll be obtaining, and also with that in mind, later on we'll be uh, constructing the phase plane, the phase portraits for nonlinear dynamic systems, and verifying the stability from the phase portraits. So for a second order linear system, whose characteristic equation is given by square plus 2 zeta omega ns plus omega n square equal to 0. You understand we'll be obtaining different roots s1 and s2, alpha plus minus j beta. Fine. And we understand for different roots we'll be obtaining different types of responses. So we have a number of cases that we actually already understand from the linear dynamics. Case 1, the case where we have pair of real, negative, distinct roots. So we have two negative roots, s1 and s2. They are real and they are distinct. This is the s-plane, and we understand if the roots are located in the left half of the s-plane, the system response is stable. And we also understand, we have studied this, that this corresponds to an output response of a overdamped system. Fine, so there will be no oscillations, no peak will be obtained in this case. Now corresponding this to a phase plane that's actually plot of x1 versus x2 will be obtaining different trajectories, and these trajectories that will be obtaining depending upon different initial conditions of the system. All these trajectories will be converging towards the origin. So depending upon different initial conditions, we'll be obtaining different phase trajectories. This complete is actually a phase portrait, and will be all these trajectories will be converging towards the origin. In such a case, the equilibrium point that will be obtaining correspond to real, negative, distinct roots, and having these types of phase trajectories, the equilibrium point is referred to as a node. And since this refers to a stable system, so stable equilibrium point, so it is known as a stable node. I'm not calling the system is stable, I'm saying this equilibrium point is stable. Fine. you understand that by now. For nonlinear systems, we can have a number of equilibrium points, and these equilibrium points, some of them can be stable, some of them may or not be unstable, may or may not be stable. So the equilibrium point in this case is referred to as a node, and since we are talking about a stable equilibrium point, so it will be known as a stable node. So whenever you'll be told that you have a stable node, so you can understand what type of phase trajectories we'll be having, and corresponding to a linear system, we can also visualize that where the roots will be for the linearized system. We can also understand what type of response we'll be having. So only by saying that we have a stable node, the phase portrait, the stability of the system is determined. Case 2, that of real, positive, distinct roots. So we have a second case. In the S-plane we have two roots located on the right side of the S-plane. They are positive, they are real, and they are distinct, not complex numbers. So this is an unstable system, and for this type of system, the phase trajectories that will be obtaining depending upon different initial conditions will not be converging towards the origin, they will be diverging from the origin, they will be moving out of the origin. The equilibrium point that we have here is again still referred to as a node, but since we are talking about unstable equilibrium points, so it will be referred to as an unstable node. So we are actually talking about linear systems. So in this case, the equilibrium point in the system actually means the same for a linear system, but since will be dealing with non-linear systems, so I will saying that the equilibrium point is unstable node. I will not be saying the system is unstable node. Case number 3, we have a case of where our roots are on j omega axis. Fine. So you have two roots, complex conjugates on j omega axis. So such a system we understand is marginally stable. A system whose characteristic equation and the response will be oscillatory. Fine. A system whose characteristic equation is something like s square plus omega n square equal to 0. 2 zeta omega n is missing. Zeta is actually 0 for n. This is actually an undamped system. Undamped response, zeta is equal to 0. So we have the characteristic equation s square plus omega n square equal to 0. So we'll be getting a pair of complex conjugate roots. And the phase portrait of such a system is actually what we have already plotted for in an example that we did in the last session. Circular plots, circles. So a graph between x1 and x2 for such a system will be a circle, and the equilibrium point in such a case is known as a vortex. You can say it is a center point or a vortex. So we are obtaining closed paths in the phase plane. One property from the phase plane that we'll see later on actually when we'll analyze limit cycles. If we are obtaining a closed path in a phase plane, in that case the system, this equilibrium point is referred to as a vortex here. In that case the system will exhibit the property of limit cycle. So limit cycle, if you remember, I have talked about this, is the property of a system wherein it starts oscillating, shows fixed oscillations of fixed magnitude and fixed frequency without any external disturbance or any input. Such systems are going to exhibit the property of limit cycle. And from the phase plane, how we can identify that? If we are obtaining a closed path. Now there is a difference here. Any closed path, every closed path is not a vortex. Only circular paths that we obtain like this is a vortex. And closed path can be anywhere in the phase portrait. It can be something like this. It can be something like this. These are all closed paths. So any of these can refer to as a the system being a limit cycle. So it's not necessary that that point there is a center point or a vortex. We'll be looking at this in detail later on. So for now, what you need to remember is if you have two roots, that's a pair of complex conjugate roots on the j omega axis, it's a marginally stable system. That means its response is undamped, oscillatory, and in the phase portrait we'll be obtaining circular paths, and this equivalent point will be referred to as a vortex. Now this is marginally stable system. Case number 4. So we have undamped systems, overdamped systems, critically damped systems, underdamped systems, and then unstable systems as well. So case number 4, we have now a pair of complex conjugate roots in left half. So you have a root here and you have a mirror image of it here. So this is a stable system again, roots in the left half. The response type is underdamped. Fine. And for such a case, you will be obtaining phase portrait like this. So depending upon different initial conditions, this is for one initial condition, this can be for second initial condition. So all those portraits that we are obtaining, all those trajectories that we are obtaining, they are converging towards the origin. In this case, that will actually be an equilibrium point. How that's an equilibrium point, we'll discuss that later. And in this case, the equilibrium point that we have is called a focus. And since we are talking about a stable system, so it will be a stable focus. Fine. Case number 5. Pair of complex conjugate roots in the right half. So we have two roots, one is located at this position, so you have S1, S2 here. So this is an unstable system, so you can have any type of response. phase portrait, again depending upon different initial conditions, we can have a phase portrait like this, we can have a phase portrait like this. So now the characteristic of these phase portraits will be, they will not be converging, they will not be moving towards the origin, they will be moving out of the origin. So we have these phase trajectories moving out of the origin. The equilibrium point is still a focus, but now we are talking about an unstable focus. So the last case, two real but opposite signed. So these will be having symmetry, not they will not be mirror image around the real axis, they will now be mirror image around the imaginary axis on either side of the imaginary axis. We have two real equal but opposite signed roots, S1 and minus S1, and this is unstable system, or a linear system having such a dynamics will be unstable. Now the phase portrait of such a system will be having curves like these. We'll be having some curves that will be moving out of the origin. We'll be having some curves that will be moving into the origin. We'll be having these types of curves that will be trying to move towards the origin but then divert. So you may have phase trajectories that are in this fashion, and this equilibrium point is referred to as a saddle point. It is an unstable equilibrium point, not marginally stable, it's unstable. So we have seen 6 cases. We have actually 4 different types of points. We have a focus, we have a node, we have a vortex, and we have a saddle point. Focus, node, vortex, and saddle points. Vortex by default it is marginally stable, it will not be anything different. Saddle is unstable. As far as focus and node go, they are both stable and unstable depending upon whether the roots are on the left half or on the right half. So focus is something where we have complex roots either in the left half of the S-plane, then it will be stable, or in the right half of the S-plane, then it will be unstable. Node is points, they are real roots, and These routes are either again they are distinct routes. They will be either in the left half, then such a node will be referred to as a stable node, or in the right half, then such a node will be unstable node. And for a node you have seen uh, the type of phase trajectories we'll be getting. For a focus we'll be having spiral, logarithmic spirals. For a node we have simple parabolic trajectories or linear trajectories. A vortex or a center point is having a circular phase trajectories in the phase portrait, in the phase plane, and they are actually corresponding to two routes that are located on the imaginary axis. Saddle point, you have you have two routes on the real routes, but one is positive and another one is negative. So it is unstable. So you will be having phase trajectories, some of which will be converging towards the origin, some of which will be moving out of the origin. Now these are when we are actually translating something that we have studied in linear system onto a phase plane. And as you have seen, I have been referring to the equilibrium points. I have not been referring to the system itself. So a system can be having all of these or can be having any one of these. Fine, any one or two, or it can have a focus also, it can have a node also, or it can have a focus and a vortex also. So how many equilibrium points? So around equilibrium points, each equilibrium point will be different. So one of the equilibrium point may exhibit the property of focus, another equilibrium point may exhibit the property of node, third equilibrium point can exhibit the property of vortex, and someone may be a saddle point. So all these properties can be in the same nonlinear system as well. So we are not be dealing with such nonlinearity is going to be very hard to find, but it can be there. So these equilibrium points when transferred, so you can have an equilibrium point that is, say for example, we have seen for a simple pendulum defined by the equations x1 dot equal to x2 and x2 dot equal to minus g by L sine theta. We have seen the equilibrium points is 0, 0 and 0 pi, actually 0 n pi, so we had actually n number of equilibrium points, and for each equilibrium point, one equilibrium point can be, say for example 0, 0, so it's fine, it's located at the origin. Another equilibrium point is 0 pi or pi 0 rather, so it's not actually located at the origin, it is located at its position. So what we do in that case is shift this equilibrium point towards the origin by translating by actually making sure that if we are actually once we are actually doing this, what we'll be doing is we'll be, instead of having, say for example, instead of using x1 we'll be using x1 bar, and that is actually x1 equal to x1 minus pi, and we'll be obtaining the state space in terms of x1 bar and x2 bar, so that the equilibrium point that was actually at pi 0 now shifted to the origin at 0, 0. These equilibrium points actually exhibit the property that where x dot will be equal to 0 and located at the origin. They are also known as the singular points of nonlinear systems. So singularity of a nonlinear system is actually where x dot will be equal to 0, and these singular points can be analyzed for any type of system. So when we'll be talking about stability in phase plane, we'll be trying to see the phase plane match which of these the properties of which of these singular points. We'll be trying to see whether the phase plane is exhibiting the property of a focus, whether the phase plane is exhibiting the property of a node, whether the phase plane is exhibiting the property of a vortex or that of a saddle. Fine. So accordingly we can then decide where the routes will be, how their output response will be corresponding to this particular equilibrium point. As I have been saying, each and every equilibrium point of the nonlinear system will exhibit different properties. So this is about, we'll be translating this to phase plane analysis. We'll be seeing that. Now what we have to do is we have to now look into the construction of phase portraits, how we can actually construct the phase portraits. So we have two methods here for construction of phase portraits. One is the analytical method, and second one the graphical method. Graphical method, you can have actually you have the isopline method, the method of isoplines. Fine. You have the delta method, and these how we can obtain the how we can construct the phase portrait using both these two methods. We'll be doing that in the next session. So this is about stability analysis in phase planes. So we have different types of equilibrium points corresponding to different corresponding to the location of roots in the S-plane, and according to each equilibrium point there is a type of trajectory you obtain, and just by looking at the trajectory you can say whether this system is stable or not. If the trajectory is moving into the origin, it is stable. If it is moving out of the origin, it is unstable equilibrium point. So that's all for this session. We'll continue in the next session.